Hello everyone, we're going to start a new unit on trigonometry. Now, trig happens to have a lot of radical expressions in it, so we're going to have to be able to simplify radical expressions in order to do a lot of the trig that we're going to work with. So even though this topic itself is not trigonometry, it's like a prerequisite to trigonometry. We got to be able to do some of the stuff in order to do trigonometry itself. So, this is a topic that is going to be discussed also in Algebra 2 if you end up going on to that course. So, let's discuss this a little bit for right now. A radical expression, you guys might notice as a square root function. That's what most of you guys call this, a square root. That's a radical expression. Okay? We actually have three parts. We have on the outside in this little space what's called an index. Now, generally speaking, on square roots, we don't see a number there. It's just left blank, our index. So we're going to assume that it means 2. Okay? In Algebra 2, you're going to see a 3 maybe, or even a 4 or a 5. Okay, that would mean that we're looking for a cube root or a fourth root or fifth root. But we're always going to be looking for a second root, which is square root. Hence, the square root is what you're used to calling it. Then we have the number on the inside, which we call a radicand. Okay, it is just the number that is in the function. And then we have the function itself, which is called the radical. Okay, the radical is really just a little check mark, division looking sign. It's an operation. It's asking us to find the second root of this number, the radicand. Alright, so we need to look at a couple of things. For a radical to be in simplest form, we want it to be in simplified form, just like we do with fractions. We want it simplified. It must meet all three requirements. The first requirement, there are no perfect square factors inside the radical. Perfect square factors. Well, look at the word factor. Key here. A factor is when you take a number and you think about the numbers that multiply to make that number. Those are factors, the numbers that can multiply to a number. We're looking to make sure that there are no perfect square factors in our radical. Okay, so when we break down this number, a, into two numbers that multiply to it, we don't want a perfect square as one of them. The second thing is that there are no fractions inside the radical. Our radicand has to be a whole number. Fractions are no good. Third, there are no radicals that appear in the denominator or the bottom of a fraction. So we are going to see that we're going to have maybe like 2 over a number. We don't want that number on bottom to have a radical. That's no good. We want to make sure that the number on bottom is just a whole number at the very least, no radicals. Now, one other thing that we're going to have to look at is the perfect square numbers. If you don't know your perfect square numbers, you need to practice these. You need to memorize them. Not only do you need to memorize them, but you need to know how to get them. Okay, a square is the result of a number times itself. So when we look at 1 times 1, our result gives us 1. 1 is the perfect square number. When we multiply 2 times itself, we get a result of 4. 4 being the perfect square. Then we have 3 by 3, 4 times 4, and so on to get each of these perfect square numbers. Now I only have the first 10. I suggest that you memorize the first 15. Okay, so the next one would be 121, 144, 169, 196, and 225. Those should probably be added onto this list for you to memorize. So we're going to be looking to see if we can multiply two numbers to get the radicand, one of them being one of these numbers. Okay, that's going to be our strategy. Okay, so here we go. We have an example here. We have the square root of 75 that we're trying to simplify. Now, we don't want to put decimals here. Okay, our final solution is going to be a number and possibly another square root with a number inside. That's all we're looking for. We don't want decimals. We want to leave it in simplified terms. Now, our strategy for all of these problems is going to be to think about two numbers that multiply to make our radicand. But we want one to be a perfect square. So we need to think of two numbers that multiply to make 75, one of them being one of these numbers. Now, this one's kind of easy because I know that 25 times 3 will give me 75. So right now we have 25 times 3 under the radical. The next thing that we have to check for is that we don't want to have any perfect squares factors inside that radical. So why would I want to break it up into a perfect square? Well, that's because this 25, now that we recognize it as a perfect square, it can leave the function as its root, meaning the number that we're going to multiply by itself to get 25, whatever the number that happens to be, will come out of the radical. That number happens to be 5. So 5 comes out, 25 is no longer there. As far as this 3 is a prime number. There's no number that multiplies to make 3 other than 1 in itself. So it can't leave anywhere. It's not a perfect square. It's stuck inside that radical. So our final solution to this problem is 5 root 3. I'm going to do one more, and I'll give you a couple examples to work on. We're looking at the number 18. Again, I'm trying to think of two numbers that multiply to make 18, one of them being a perfect square. Here are my perfect squares. Well, 9 times 2 gives me 18. So 9 times 2. I have two factors, one of them being a perfect square. That's good because I'm going to take that 9 out as its root, which is 3. The 2 can't come out, so the 2 stays inside, and my solution is 3 root 2. So here are a couple more examples for you to try. Oops, I can't actually see them. There we go. Take a second to pause the video and try this on your own. Alright, let's see how you did. When I'm looking at 12, I'm thinking of two numbers that multiply. I'm thinking 4 times 3. 4 is one of my perfect squares, right? Here's my perfect squares. So the root of 4 comes out. That happens to be 2. 3 can't leave yet. So my final solution here is 2 root 3. Looking at 98, this one might have been the tricky one for you. Trying to think of two numbers that multiply to 98, one of them being this perfect square. So let's say that you had trouble with this one. Let's say that you couldn't figure out what numbers to use. Well, here's what I would suggest. Take a calculator, right? And I'm going to type in the number that I'm looking for, 98. And I'm going to divide it by some of these squares just to test. Let's see if 98 is divisible by, let's say, 16. If it is, when I press my solution button, I will end up with a whole number. If I don't end up with a whole number, like I've got decimals over here, 98 is not divisible by that perfect square. So I'm going to try a different number. I'm going to try 98 divided by, well, let's see, 25 definitely won't work. Let's try 36. No good here either. So let's try the next one. 98 divided by, let's try 49. Here we go. 49 is my perfect square. I got a result of 2, which is a whole number. So the numbers I'm going to use are 49 times 2. If that was confusing, take a second to rewind this video and listen to that again, because we really want to make sure that we're looking for the right numbers here. And if you can't figure that out, you're going to have to do a little bit of testing to see what numbers work. Okay? Anyways, our 49 is going to come out as its root, which is 7. The 2 can't go anywhere yet. So our solution is 7 root 2. All right. Next thing that we're going to look at is something called the product property. Now, I actually wrote this backwards, but it's not really a big deal. It's going to work either way. It tells us that if we're multiplying two radicals, we have the ability to just put them underneath the same radical, and it's going to come out to be the same thing. For example, root 3 times root 2 is the same thing as root of 3 times 2, which ultimately gives us the square root of 6. Okay, so that's just an example of how this works. We can also break it up. If we start with a square root of 6, we can think of two numbers that multiply to it, and then we can break it up into individual pieces. Okay, so that's all the product property lets us do. So let's look at an example here. We want to simplify. Well, we only want to have one radical. So this is going to give us 15 times 3, which is equal to 45. But we still want to see if we can simplify this thing. I need to think of two numbers that multiply to 45, one of them being a perfect square, and I'm thinking 9 times 5. 9's my perfect square. 9 times 5 is 45, so it all works out pretty well. That 9 is going to come out as the root, which is 3, and our 5 remains. So we started off with root 15 times root 3, and we ended up as 3 root 5, just by using the product property and simplification methods. Okay, here's one for you to try on your own. Take a second to do it out, pause the video, and then come back. Alright, let's see how you did. 12 times root 12 times root 2, right? We can put it all under one radical. That's going to give us a result of root 24. And I want to think of two numbers that multiply to 24, one being a perfect square. What I'm thinking of here is 4 times 6. I could have used 8 and 3, but 8 is not a perfect square, so I don't want to use that. I want to make sure that I'm using a perfect square. The root comes out, which happens to be 2. 6 does not break down any further, so I'm going to leave it alone. My solution here is 2 root 6. We'll also have something called the quotient property. Okay, the quotient property is exactly the same idea as that product property, only we're using quotients, which is a fancy math term for fractions. Okay, we have the square root of a fraction, a over b. What the quotient property allows us to do is it allows us to break it up into two separate problems of square root of a over the square root of b. This is nice because we can work individually on the top and individually on the bottom, and then later on we can do some elimination to simplify it even further. Okay, so here's an example of how this works. We have the square root of 2/3. We can break it up to the square root of 2 over the square root of 3. Okay, let's try checking one out down here. Our first example, square root of 16 over 25. Well, that's not too difficult. We got the square root of 16 over the square root of 25. 16 is a perfect square, so its root of 4 comes out. 25 is also a perfect square, so its root of 5 comes out, and that is as simplified as it can go. That's our solution. Looking at another example, here we have 32 over 50 all under the radical, so I'm going to split it up into two smaller pieces. Now, neither of these are perfect squares, so I'm going to have to think about numbers that multiply to get these, just like we were doing before. So 32. Well, 32 is 16 times 2, 16 being my perfect square, and 50 is 25 times 2. Again, I have perfect square. The root of 16 comes out, that's going to be 4. Root 2 stays. 25's root comes out as 5. and root 2 stays. So right now I look like I have an answer. However, I should notice that I have root 2 over root 2, which can reduce. Those two eliminate each other, and all I'm left with is my final solution of 4 over 5. I have 2 examples down here for you to try. They shouldn't take you too long, hopefully, so give them a shot, pause this video, and resume when you're ready to check. Alright, let's see how you did. We're going to break these up into 2 different pieces. Square root of 25 over the square root of 100. Square root of 25 comes out as 5. Square root of 100 comes out as 10. Hey, this can reduce. That's going to reduce to 1/2. Hopefully you got that one. Now we're looking at a different one. I got to think of numbers that multiply to both 12, and I need a number that multiplies to 75. The numbers that I thought of were 4 times 3 for 12 and 25 times 3 for 75. Okay, 4's root comes out, gives me 2 root 3. 25's root comes out, gives me 5 root 3. And again, I should notice that my root 3's on the top and bottom will eliminate. My final solution here is 2 over 5. Alright, we have one more thing to discuss. If you remember at the beginning of this 17-minute long video so far, okay, at the very beginning it mentioned something about no radicals appear in the denominator, the bottom of a fraction. Well, what happens if we end up with that situation? We have to do this thing called rationalizing the denominator. Remember, no radicals in the denominator. So here's an example. We get 2 over 3 under the radical, and we break it up so we have root 2 over root 3. Well, this is all good except for the radical. So how do we get that out of there? Well, this is it, guys. We're going to multiply this by 1. Multiplying by 1 is perfectly legal because when you multiply by 1, the initial number doesn't change, right? For example, 10 times 1, we still get 10 as a result, so we never change the 10 by multiplying it by 1. Well, we're going to multiply by 1, but we're going to do it in a really fancy or sneaky different way. Here's what I'm talking about. We're going to multiply by a fraction. And as long as we have the same number on top and on bottom, it's going to give us a fancy looking 1. The question is, what do we want to multiply by? We're going to multiply by whatever our denominator happens to be. We're going to multiply by the square root of 3. But again, because we want this to look like a 1, we're going to do root 3 over root 3. Why would I want to choose that same radical, though? Well, let's think about it. The product property tells us that when we multiply these two things, we can put them underneath the same radical. Okay, so here we have now root 2 times 3 times root 3 times 3. Well, that's going to give us the square root of 6 on top, and down here we should notice that we have the square root of 9. The square root of 9 is a perfect square, which comes out as 3. Okay, another way of looking at this same thing is that we have 3 squared, right? Because we have 3 times 3. The square and the square root are inverse functions. They cancel each other out. And what we're left with is the same 3 that we started with. Okay, so either way you want to think of this. Either we multiply, get our square, and then reduce it to its root. Or if you think about this as being numbers squared and inverses, it's going to give you the same result. So that's why we're choosing to use the same radical to make our fancy 1. Okay. And yes, I do call it a fancy 1. Okay. So, here's an example for us to look at. We have 2 over root 2. Again, we want to multiply by that fancy 1 that we're going to create using whatever number is in the denominator. So root 2 over root 2. Well, that's going to give us 2 root 2 on the top, and we're going to have 2 squared under a radical on bottom. That radical and square are inverses. They eliminate each other. That means we have 2 root 2 on top over 2. Ah, I see that my 2's can cancel each other out, 1 on top, 1 on bottom. That leaves me with plain old root 2 for my solution. Okay, looking at another one. I have square root of 5 over square root of 11. I want to multiply by that fancy 1. Root 11 over root 11. That's going to give me, well, I'm going to have root 5 times 11 and root 11 squared. I should notice that those eliminate. 5 times 11 gives me 55, still under the radical, and 11. 55 does not simplify. That's as simple as 55 gets. So we're going to have our solution as root 55 over 11. So I have 2 more for you to try out on your own. Okay, this has already been a pretty long video, so try them out, pause it, and see how you did. Okay, let's check these out. I have root 7 over 27. I am going to break this up into smaller pieces, and then I need to think about numbers that multiply to 27. Well, I know that 9 times 3 works, and I know that the 9 is going to come out, so I have root 7 over 3 root 3. The question is, what do I want to multiply by to get rid of that root 3? I'm only going to multiply by that radical. So radical 3, radical 3. So this is what's going on here. I have root 7 times 3, and I have 3 times the square root of 3 squared. That's going to eliminate, and I'm going to keep that 3 that just came out. 7 times 3 is 21. Now I have 3 times 3. My final answer is the square root of 21 over 9. 21 is as simplified as it can be, so that is, in fact, our final answer. So if you want to try this one more on your own, see how it goes, let's check it out. Root 5 over root 18. I'm thinking 9 times 2 for this 18. The 9 is going to come out as a 3, so I have 3 root 2 in my denominator. My numerator never changed, but now I got to do something to get rid of that square root of 2. So I'll use my fancy 1 made up of a root 2 over root 2. That's going to give me root 10 on top, right? 5 times 2. Down here I have 3 times root 2 squared. That squared goes away. That gives me root 10 over 3 times 2. And all I have to do is just think about this. 3 times 2 becomes a 6. So my final answer here is root 10 over 6. Okay, root 10 does not simplify any further either. This is, in fact, my final solution. Alright, so this was a pretty long video. I would suggest maybe watching it again if you're having difficulties with it, or bringing any questions you have into class or on the website, and I'll do my best to answer them as soon as I can.